Gravity makes time run slow, and here's how. What I've drawn here is light, perhaps a laser beam, being pointed up from the surface of the Earth out into space. And as it climbs higher, it has to lose energy. But it can't lose energy by slowing down, as would happen to a ball that you throw up in the air, because light always travels at the speed of light. Turns out the only way that light can lose energy is to stretch out into a longer wavelength. So that's why I've drawn the light this way, and this is based just on conservation of energy so far. So where does time come in? Well, we're going to build two identical clocks at the bottom, and we'll calibrate them. For convenience sake, we'll say that the wavelength of light down here coming out of the laser is 1 foot. And light travels at about 1 foot per nanosecond. So these clocks will tick once per nanosecond. So for every wavelength of light coming out of this laser, the clocks tick once. And those numbers are just for convenience. You could use any numbers. The argument is the same. What we're going to do now is move the second clock up here to the top. Now what happens? The wavelength of light up here looks to be about 3 times as long as the wavelength when it was coming out of the laser. So if 3 times the length of light have to slide by this clock, then 3 times the number of ticks have to go off, because the clocks are identical, right? So far there's nothing really tricky. We're just saying the wavelength down here was 1 foot. So in the time that 1 foot of light goes by, this clock ticks once. In the time that 3 feet of light go by, this clock ticks 3 times. Those are identical clocks. So far, nothing tricky. The tricky part is to realize that a wavelength coming out of here, out of the laser, 1 second later it becomes the next wavelength up here, which is slightly longer. And 1 second later it becomes this wavelength, which is even longer. And 1 second later it becomes this wavelength. So in the time that it takes for one new wavelength to emerge from the laser is the same time that it takes for a big wavelength to slide by up here. So that means that the time that it takes for 1 tick to go by here is the time that it takes for 3 ticks to go by here. In other words, the clock at the top is running faster. The clock that feels the stronger gravity is running slower. So gravity actually makes time slow down. And the amount of this slowing down is quite small. On the Earth it's very, very, very small. But near a very strong source of gravity, such as a black hole, the wavelength of light can be much increased by the time it gets very far away, for example, to astronomers' telescopes on Earth. So this gravitational redshift effect is key to understanding that gravity makes time slow down.